Hi, Professor Yu.
Good to see you.
Yeah,
So
good
sorry,
afternoon.
maybe because that Zoom
Hi.
account is in China. Sorry about it.
Yeah, no problem. Yeah. Welcome to our webinar. Thank you very much.
Thank you so much. Thank you.
Yeah. Don't worry about that. We are now, this time is 33:58, okay, PM. So it's good.
Okay. That's good. So you're on site, yeah. It's a conference on site. You have students or some the faculty members?
Maybe about nowadays there are 36 attendants. Professor and student, okay?
Okay. No,
36
sure. No.
attendants here.
Okay, good.
36, 32 or 36. Yeah, 37, 38. Too many.
No problem. No, it's
don't worry about it. Yeah.
It's
Okay.
very good. Yeah, I'm very glad to discuss with you and also your faculty members.
Okay. You see, everyone is here. Yeah, let's get started. Okay. Good afternoon, everyone. Yeah, first of all, thank you very much for attending our first webinar today from the Carbon Neutral Institute. So, and many students and professors are attending, about 48 students and professors are attending now. Okay, thank you very much. And I would like to especially thanks to Professor Jingbi You for accepting our invitation. Okay, and today, everyone know about him if you studied about the perovskite solar cell. I would like to briefly introduce his CV. He received PhD in Institute of Semiconductor, Chinese Academy of Science in 2010. And then he had postdoctoral fellow in UCLA, and his advisor was Professor Yang. And then now he is professor at Institute of Semiconductor of Chinese Academy of Science since 2015. As I said, he is very famous scientist in the perovskite solar cell. His first outstanding achievement is the introduction of passivation layer using the PEAI. PEA means phenylethyl ammonium iodide. If you use this kind of passivation layer, you can reduce defect density with the iodide vacancy, so increased our VOC or fill factor to make high efficiency perovskite solar cell. So this is very powerful method until now. And also his second outstanding achievement is to use the tin oxide based electron transfer layer in the perovskite solar cell. Many other scientists, including me, at that time, until that time, many other scientists, including me, we have used usually titanium dioxide based electron transfer layer. But he is a pioneer, I think. He is a very excellent scientist to use the tin oxide based electron transfer layer since then. So nowadays, most of the scientists use the tin oxide based electron transfer layer in the perovskite solar cell. Okay, this is a good opportunity to have a good presentation from him. And also, okay, here is a presentation topic. Here topic is efficient perovskite solar cell and light emitting diode. Please give him a round of applause. Okay, thank you.
Thank you so much. Thanks, Professor Kim's kind invitation to join these carbon neutral sessions. Actually, the carbon. Can you see the slides? No. So the carbon neutral is also very important in China because maybe you know in China our chairman called in 2035 we should reduce the cost of reduce the carbon emissions. So I think today my talk is efficient perovskite solar cell and also emitting in the science purpose chemistry kind of was on our previous work. I'm working mainly in the perovskite solar cells. I think the UNIST, every people maybe in the perovskite solar cell know the UNIST is the leading university in the perovskite solar cells. And I also need to be working on the 90 million diodes because these two type of solar cell and 90 million diodes maybe the basic mechanism is similar. So I work in these two areas. So today the topic is the first one. I will briefly introduce the development of the solar cells and also the perovskite solar cells and also the light emitting diodes. And the second, I will mainly talk about the efficient hybrids. We call hybrids is organic, inorganic hybrids. And also recently more and more people pay attention to the inorganic, the fully inorganic perovskite solar cells. And later I will talk about the efficient green and blue perovskite light emitting diodes. So the solar cell, what's the solar cell? I think what people working in your department maybe is very familiar with this background. I just briefly talk about it. This is a typical solar cell structures we call the PN structure or PIN or NIP structures. The core structure is the PN junction. Is when the p-type materials and n-type materials contact with each other, they are bending and they are bendings. So they have building-in potentials and building-in electrical field. This electrical field is very helpful for the charge separations. When the lights emulations the materials, they induce the electrons and holes. And underneath building in electrical field, the charge can be separated. So this and the current can we can get the current, and also we can get the open circuit voltage. This is the basic, so we can get the output. So this is the basic principle of the solar cell. So the solar cell is the device, is the semiconductor device can convert the sunlight and into the electricity. So for the PV photovoltaic, for the solar cells, the technology, this is briefly histories. So I think the first generation we call the single crystal silicon and the single crystal gallium arsenide. The single crystal silicon maybe now is very popular in the solar cell, and most of close to 95, the market is by the silicon solar cell. And also in the Army, we have the multi-junction of gallium arsenide. So this is the very thick, maybe several hundred micrometers to use the active layer to absorb light. So more and more people realize should we reduce the thickness to reduce the cost to make it nice and high efficient. So at that time, people try to deposit amorphous silicon film, very thin layer to make efficient solar. However, the amorphous silicon is not stable because it should use the hydrogen to stabilize the silicon, amorphous silicon. So later, people invented CIGS or CDTE. CIGS is 4 inorganic elements to make this is very complicated. Now because the indium is a rare metals, so it's very expensive. So for the CDTE, and I think every people, if you work in the solar cell, maybe know the very familiar with the company First Solar in USA. Maybe most of the solar cells used in USA come from the First Solar. So anyway, all of these materials is based on the inorganic materials. So all of the material, the deposition should be the high vacuum, high temperature to deposit all of to make the device. So people it's always thinking about how can we design a new type of solar cell to reduce the cost and to make it very easy, simple processing. So I think I have browsed the faculty members in the UNIST in your department. I see some of the civil faculty professors working in the organic solar cell and also in the perovskite solar cells. It's very powerful in these areas. So I think this is also consistent with our work. So people, or most more and more people realize, can we design the very high efficiency, no cost, and the flexible solar cell to apply application in our daily life and also in the army. I think in our histories now we have several attempts to design low cost and a new type of we call it emerging PV. So the first one is the Dyson size solar cell. This type of solar cell is very popular in 1919 to at the beginning of 2000. I think at that time, the device structure is maybe it's very similar at the beginning of the perovskite solar cell. They use the mesoporous titanium oxide, and the dye was absorbed on the titanium oxide surface. This is I think this is the very simple PN junctions. So the material, the dye absorb light, and then the charge extraction or charge separation at the titanium oxide surface to titanium oxide was responsible for the electron transport, and iron was responsible is similar to the whole transport layers. So this is the titanium oxide, the Dyson size solar cells. And another type is organic solar cells. And actually, when I was a postdoc in UCLA, at the beginning, I worked in the organic tandem solar cells. So the the key point, the organic PV, the PV is the bulk hydrogen junction, it's blended donor and accept. Maybe it's similar as the PN junction. We mixture these two materials together due to the limitation of the charge transport properties, and also to enhance the charge separations. So I think even though there's several very important progress in the two type of solar cell, I think at present the Dyson size solar cell efficiency may be close to 13 or 14. The organic solar cell now is close to 20. Only two type is still less than 20. So can we build a dream is that can we build a new type of solar cell is close to the inorganic semiconductors. So I think now I think the UNIST has created a new what we call the 25.7. It's the perovskite solar cell. I think maybe there should be more progress in these areas. This efficiency is very important because it is close to silicon solar cells. So this is the wonderful materials in PV technology. And Professor Miyazaki from top university of in Japan has applied these materials in the solar cell at the beginning in 2009. I think after more than 10 years development, more and more people realize this material is excellent photovoltaic materials. I think there are several advantages if people work in this area. So the first one in this type of materials is good absorption materials. If we like to make the thin film solar cell, we should have good absorption coefficient. For the first generation, the solar cell materials such as silicon, this is indirect band materials. So the absorption coefficient is very limited. So we should use more than 200 micrometers to absorb the light. So the second one is the gallium arsenide, because the S type is the density of state is very limited. So the absorption efficiency is also limited. So perovskite materials is very unique, and there are some strong optical coupling. So the density of states and conduction band and the valence band is very high. So the absorption coefficient is very high. So we should just need less than 1 micrometers to can absorb all the light in its band gap regions. So the another advantage in these materials is highly defective tolerance. Because this material, when we use the solution process, the material, the film we obtain is the multicrystalline. So there are several boundaries and also the several defects. Or if we just use a very simple spin coating, we can get easily over 20% efficiency. So this material is so we can see that this material is a highly defect tolerance defect. So most of the defects is the shadow defect. The deep states of defects is harder to form because the high energy formations. So this is the comparing with the perovskite materials with the traditional silicon CIGS and gallium arsenides. We saw some of the property is close or even better than the traditional inorganic materials. So I think this is the summary of the present status of the perovskite solar cells. As a solar cell, we pay attention to 3 facts. We call it the golden triangle rules. The one is efficiency. In the lab, we can see this is a very fast development of the perovskite solar cells. As the highest efficiency I have mentioned 25.7 for the certified efficiency. And in 2018, we have got 23.3 and 23.7. Now we can get close to 25.7 efficiency. And it's not lab efficiency, we call it small region, small area efficiency. So the second one is the scale, and so we can we saw is the cost. We should reduce the cost. And now the highest efficient Panasonic is 800 centimeters square and it's close to 18. I think the Professor Kim also had worked very good works in the large area devices last time had mentioned. And the last one is stability. People are concerned about the stability. How can we make a perovskite the device more stable, and how can we compete with the traditional silicon? So the stability is the last bottleneck for the efficient make it commercialized. So anyway, so and another one is the perovskite is also a good emitting materials. And I think for the solar cells, we need the nut crystal to make it to no green boundary, and also to increase the charge diffusion length to make sure that when the charge induced, they can very efficient to separate. However, for the light emitting diodes materials, we should confine the charge in the small areas and to make it recombine as soon as possible to make it to emit. So when we make an efficient perovskite light emitting diodes, we should reduce the crystal size. Maybe sometimes we synthesize the nanocrystal, sometimes we use the quantum structures to confine the charges. So these materials also show the very good emitting properties, such as the tunable band gap and very high PUKY, close to 100. And the emission widens is very small, it's very narrow to less than 20 nanometers. It's very good for the high resolution and bright emission materials. So this is the progress of the perovskite light emitting diodes. And now the emission efficiency for the green and also for the infrared red is over 20% efficiency. And the blue is a challenge. I think it is catching up of the blue and red. I think every type of the light emitting diodes, the blue is always the challenge. So let's talk about our work in the efficient hybrid and inorganic perovskite solar cells. I have a brief summary of the efficient progress in the perovskite solar, the hybrid perovskite solar cells. I think, and the Korea has great contribution into this field to developing high efficiency perovskite solar cells. I think the first stage is how can we control the crystal growth? How can we get high quality of the perovskite film to reduce the boundary, to make the film smooth and not crystals, and no and as small as for the pinholes. So this the stage one, the growth of high quality of perovskite film is similar as the inorganic source. We should not crystal and reduce the recombination and others. This is the first stage. And the second stage is the charge transport layer. Oh, it may be some shift. The charge transport, the control. Because at the beginning, this type of source is coming from it's initially designed from the Dyson side solar cell is the missile cross structures, and also some charge transport problem. So how can control the charge transport is the second stage. And the third stage, I think, is the defect pacifications as from the process stroke, and also done a lot of work in the pacifications. And also the UNIST has designed a bi-layer electron transport layer and or the coherent layer for the perovskite solar to make it efficient. And also we have done a little bit of work in the interfacial pacifications to make it efficient solar cell. I think the high efficiency perovskite solar cells is the first stage is how can we control the growth of the high quality of perovskite films. I think that the first examples the Professor has developed and coil evaporations to make a thin film, make the condense and pinhole free perovskite films. And this has made us believe if we can grow very high quality of perovskite films, we can get high efficient, high performance. And also some guys have developed two-step depositions to make use the diffusions and two compound to diffusions and to formation of the perovskite films. I think from in our goal, most of the work to focus on how can we get the high quality of perovskite film by this two-step depositions. And another great contribution to this field is the fast anti-solvent. If we can to confine the liquidation and to maybe very fast or to form intimate of the phase to make the high quality of perovskite films. Actually, I think we have at the beginning, we have followed some work and also had some our thinkings. I think this is the link to across our research. When I was a postdoc in UCLA, every people at the beginning believed the perovskite materials growth should be in the nitrogen or the inlet environment because the perovskite material is very sensitive to the moisture, to the water. So because the water can decompose perovskite materials. However, at that time we found if we thermal perovskite processes, if we after spin coatings, we take it out to the environment, into the ambient environment, we can see the perovskite film to the transparent to the dark. This means the molecule can induce the perovskite growth. So based on the link, we are needing the perovskite in the several environment, for example, in the dry nitrogen environment and in the dry oxygen environment. And also based on our finding because these materials could induce the perovskite formation in the humidity environment. So we are needing the perovskite materials in ambient air with some humidity. For example, we found optimized conditions 30 to 40. We can find this material when we are needing in the ambient air environment with humidity. The green growth is very good. So based on it, we can make high efficiency perovskite source. Actually, we use this method up to now in the two-step depositions. We always are needing the perovskite materials in the humidity environment. So the second stage, the control of the charge transport rate. This is very famous papers from the Perovskite group. They have they point out if we in the planar structure of perovskite source, we can find the series histories. We see the reverse scan and the forward scan. The efficiency totally different. If they introduce a very thin, maybe 100, 200 nanometers mesoporous structural titanium oxide, they can reduce the history. So at that time, every people believe the mesoporous or called the non-structural titanium oxide is very necessary to make histories-free perovskite solution. I was the background in the organic solution at that time because some people found if we use the inverted structure, use the PCBM as the N type of the electron transport layer to extract of the electrons. So the histories can be reduced almost the reverse and the forward, the IV almost overlap. This means because the PCBM is a very good charge, the electron which can withdraw the electrons. So this means give us ideas. So if we can find the new materials can extract the electrons very efficient. So maybe we can also reduce the histories. So at that time, we found some group had also worked in the tin oxides because tin oxide has been used in the Dyson size also how it failed because tin oxide is too conductive and too much the point defects. So and also the conduction band is not good for Dyson source. So however, the tin oxide may be good for the perovskite source because the tin oxide has a deep conduction bands and has higher electron mobility than the titanium oxide. So we try to use the tin oxide into perovskite material solar source. We just by the commercialize the tin oxide nanoparticles to incorporate into perovskite solar source to replace the titanium oxides. We found almost the histories can be almost to separate. And that time, some people also found if we modify the titanium oxide by the chloride, they also can reduce histories. However, also found that after chloride, the treatment of titanium oxide, the conduction band also shifted down. So this result can confirm if we can found the new electron transport layer, we can reduce the charge accumulation at this interface. We can reduce the histories. I think just the first Kim has mentioned now, the highest efficiency of perovskite sources almost based on the tin oxide. I think the correct, and also the UNIST has a great contribution to the CBD deposit, the chemical-based deposition of high quantity of tin oxide in these areas. And recently, Professor Kim has also to the conformal of the titanium oxide and tin oxide, because on the rough surface, especially for example on the FTO surface, the surface is very rough. How can we growth conform of the electron transport lane, because the electron transport lane is very thin. If it is not conformal, some place maybe such as like this sites maybe could induce the leakage, and also as a result reduce the device performance. If we can make it film conformal growth, even though the electron transport layer is thin, however, it still worked very well. So based on this idea, plus Kim has also knowledge in champion devices in small area and also demonstrate high efficiency of large area modules. The second stage is the defect passivation and others. I think the passivation, as I have mentioned, the perovskite material is high tolerance of the defect. However, it doesn't mean the defect is good for device. If we would like to make it very high efficient to close to these limitations, so we should try to avoid the defect recombination as good as possible. So for the device aspects, so why the defect is detrimental for the device? Because this is the VOC. VOC, we call it open circuit voltage, is the very key parameter for the solar cells. This is the J0. The J0. J0 is very sensitive to the recombination. If the recombination is high, the J0 is high, and then led to the small open circuit voltage. So we need to avoid defect related recombinations. So this is very classical examples. I think several people had working on this area. If you had experience in the perovskite solar cells, if you want to make high efficiency of perovskite solution, you should try to add a little bit more lead iodide. Why? Because some people found, if, for example, in our research study, if we overheating the perovskite film, and the perovskite will decompose it a little bit, and there were some white particles formation at the grid boundary. These materials is lead iodide decomposed by the perovskite materials. So why this material is good for the device performance? So this is the band structures. This is the perovskite, this is lead iodide. Perovskite material, the band gap is 1.5. The lead iodide is 2.3. These materials can form a type 1 band alignment. So the charge, the electron and holes cannot easily combine at this interface. So the grid boundary passes the defect related recombination should be suppressed. So as a result, if we introduce the lead iodide grid boundaries, the lifetime will be increased. We can so if more and more, for example, ABCD, more and more PBI2 form on the grid boundary, the lifetime will increase and increase gradually. So, however, we found a phenomenon is that the descent to access lead iodide, maybe it's good for the device performance, even though after several times running and measurement, the device can keep its almost initial device performance. However, if too much access the lead iodide formations, initially the device performance is very good. It's close to the little bits lead iodide access. However, when you measure the device, for example, applying the voltage, applying the sunshine, the sunlight, the sun illuminations, the device performance, we can see the device performance gradually decrease. So this is give us a link. So the this material, lead iodide, maybe it's good for device performance. However, maybe it's not good for device stability. Later, I will discuss more about this. So the second one is the passivations. So we have the people have found the net iodide can good formation passivation in the green boundaries or in the bark. However, there also still a lot of the defect on the surface because the surface is when we hitting the perovskite materials or precursors, maybe this led to some elements or ions or evaporated and led to some point defects. The defect mainly is the iodide vaccines. So how can we try to avoid the surface recombination? Actually, in the silicon solar cell and also the gallium arsenide, the silicon solar cell, some people use the silicon nitride, silicon oxide, or something like that to passivate the surface to reduce the surface recombinations. And for example, the gallium arsenide uses some white band gap, the aluminum gallium arsenide to passivate the surface. So I think at the beginning there are several people to found to develop the passivation of the materials for the perovskite materials. We found in our system is very strange phenomena. We just spin coating on this iodide organic molecule on the surface. We found without any treatment, the device performance is wonderful. However, if you heating, the device performance reduced. I think our idea at the beginning, every people believe that if you heating, there's some two-dimensional perovskite film could be formed because the PI could react with net iodide. Because last page we have showed that some white dot is PBI2. PBI2 could react with PI to form a two-dimensional perovskite on the surface. However, our device, our result is totally different. We saw this organic molecule itself can passivation the defect, can increase the VOC loss. So based on this idea and the result, we can confirm the recommendations in these materials in the perovskite films has been totally reduced. And also when this device working as a light emitting diodes, the emission is very bright and the emission is high at that time. Why should get this light emitting diodes the information? Because light emitting diodes is related to the radiative recombinations. If there's some defect in the perovskite film, the radiative the recombination will be reduced. The non-radiative recombination will increase. So the emission efficiency should be done. And then we can use this method to confirm the defects. The related recombination had to be separated. So at that time we get a 23.3 certified efficiency. And the other one is our recent work. So we actually at the beginning when working into these two steps of the perovskite, the receive. We always found the PBI2 can form on the surface. And also always found this PBI2 is not good for the stability because there's some previous results confirm if the PBI2 and the night illumination or on the UV nights, gradually there are some black color form on the surface. The black materials is the net. So this means the PBI2 could be decomposed into the net. This net, if the PBI2 decompose the net, and there will be more and more perovskite decomposition into the PBI2. So the perovskite material, the system should not be stable. So how can we make it stable? So we always think about how can we reduce net iodide and the green boundary and also make another second phase. We call it net iodide is the second phase. The perovskite is the first, is the main materials, and net iodide is the second phase. How can we reduce net iodide or convert net iodide into another materials? So we tried several materials. We found the RB chloride into the perovskite materials. We can see this white dot has been reduced a lot, and also new flag has been formed on the gray boundary surface. So we try to see what has happened. We see in these regions there's no nitrogen. So this no nitrogen means there's no hybrid perovskite formation on this interface, on these gray boundaries. And we also confirm maybe these materials is related to the combine with the lead iodide and RBCl to form a new materials. These materials we use the powder to simulation and the film simulations, and we confirm it. And also the most important, we have say the perovskite materials is this second phase improve the stability. As I think, if there's some net iodide green boundary, if perovskite is graded, if the net iodide is decomposed and the perovskite will be gradually decomposed, then more and more net iodide will be formed. If we form a new phase, this phase cannot be decomposed, and it cannot trigger the perovskite decompose. So we can find other heatings. This we call PIRC films show the much better thermal stability. And also we can find the ion aggregation's active energies is increased enough. Why? We have just a simple picture to explain these results. For example, this is two types of when we deposit FAI on the PBI2 surface without any heatings, we can naturally convert it partially to convert into the perovskite materials. However, if we deposit the FA on this secondary phase, it cannot easily to convert it to the black phase of the perovskite. This means, for example, if we in perovskite layers, if there are some PBI2 here, and when sometimes the perovskite and the heatings and the perovskite in this place, the perovskite decomposes. There's some FAI could be moving into this place to combine with the net iodide. This led to the ion aggregations and then. However, if at these sites, the perovskite, the materials from perovskite cannot react with the sites, the ion migration could be suppressed. The materials cannot be moved easily. So there could be no pathway for the ion aggregations. So this is just a simple explanations how we need to make a more solid experiment to confirm our assumptions. And then also after reduce the amount of the PBI2, we can they reduce the band gap. Why? Because the simple explanations of the PBI2 is wide band gap materials. So the PBI2 incorporation could enlarge the band gap. Or maybe because this is alloy, so maybe the other explanation is because the PBI2 and the net perovskite form a type 1 band alignment. There's some strong confinements at the gray boundary, so this led to the band gap enlargements. However, if we reduce the PBI iodides, and this confinement will be reduced and the band gap will be reduced. So the reduced band gap will be increase the short circuit current a little bit, and then also this second phase can lead to the very long diffusion at the lifetime. So based on this strategy, we get the get the 25.6 certified efficiency, and also the improved thermal stability, and also the storage stability. I have to mention the wider storage stability has been increased. The first one, if we have found, if for the some fresh devices for the some of the without the RBCL in the doped the perovskite, at the beginning, most of the devices can keep the very good histories free. However, after the storage, the histories should become larger, because everything, because when you storage, the sum of the perovskite maybe is not stable, maybe gradually to decompose the net iodide. Although net iodide is good for performance, however, too much of net iodide will lead to the ion migration and also large histories. So this is our strategy can suppress net iodide formation and can keep almost the histories is almost the same. Or I should maybe increase the rates. And the second one is the efficient inorganic perovskite solar source. The inorganic hybrid perovskites, there's some problem maybe because this material, some of the material such as the MIPBI3. These materials we can say is organic molecules. It's very too easy to evaporate during the heating or lighting. So people think about, can we totally remove this organic molecule into the inorganic? So this is what, of course, will lead to the good thermal stability. I think the phase stability is another issue. I will not discuss the here. And another one, people found this material is the high migration barriers, because when we shine these inorganic materials, and that shining of the high migrations cannot be reduced too much. However, for the inorganic perovskite material, if we and the dark maybe is very weak, the ion aggregations barrier is very high. However, when shining the device, the ion aggregations, the active energy is very low. It's close to room temperature active energy. So it's very dangerous. It means the ion aggregation will become very serious when not shining the inorganic perovskite materials. So this, from these two aspects with the inorganic materials, maybe it's the way to make it efficient and stable perovskite solar source. However, these materials, the typical materials, net iodide, the band gap is not good for the single junction. Anyway, another one is these materials led to the service, the recommendations on how can we evaluate. For this type of solar cells, most of the VOC loss is over 0.5 or 0.6. However, as we know, for the inorganic and organic hybrid perovskite, the VOC loss is 0.3. So this means it's too different. In the inorganic perovskite, the service recommendations. Maybe one is this is wider band gap materials. If the band gap is wider, and maybe the deep defect can be more easily formations. So this is should be the problem we should avoid. So how can we reduce the recombination and interface and also the bulk? The first one, we introduce some insulate materials called lithium fluorides on the surface and tin oxides. We can easily increase open circuit voltage and also demonstrate these inorganic materials and the light illuminations is stable. Recently, we got another work for the safe surface with constructions for the inorganic perovskite materials. If we look into the literatures, and most of the inorganic perovskite materials lifetime is less than 100 nanoseconds. However, in the inorganic perovskite, we can get over, for example, 5-6 microseconds for the lifetime. The non-lifetime means if we use the non-lifetime means that the charge can survive for a long time and means can very easily to collect by the electrodes. If the lifetime is too short, maybe it will be very easily to recombinations. So we found a new way to increase the inorganic perovskite's lifetime to 700 nanoseconds. So based on this method, we can see if we treatment the inorganic perovskite surface, we can do some gold colors form on the surface that we can form a new phase on the inorganic perovskite materials. Based on we can get close to 1.25 or 6 voltage or for the inorganic perovskite source, we can get over 21% efficiency. I think that it is the I think that I'm not a good expert in the to predict the directions. I think the UNIST is the leading scientist in this area. I think for the future for the solar cell, I think the one is the ultra high efficiency single junction. I should be it's better than silicon solar cell for the laboratory the efficiency. And the second one is the perovskite based tandem. I have not mentioned in this area. Also, we have working on this area a little bit for the not only for the perovskite tandem and also the perovskite silicon or with other material the tandem. And the third one is large area the perovskite modules. So how can we make very smooth? We can very uniform high quality perovskite films in the large areas for the commercialized and for the industry. And I think the last one is long-term stable. How can we make sure the perovskite can survive for 10 years or 20 years? This is the future direction for into these areas, and also some change and also some challenges in these areas. The last one I talk a little bit about our work in the efficient perovskite light emitting diodes. I have to still mention is the defect. How can we make efficient the perovskite light emitting diodes? I think for the perovskite materials, we always talk about the defect recommendations. For light emitting diodes, we should make sure the charge, the hole and electron can be combined and as the radiative emissions. So we should reduce the recommendations, the non-radiative recommendations. So as the experience in the solar source, we also have transfer the technology in the solar cells into the light emitting diodes. The passivation is always important for the light emitting for solar cells and also the light emitting diodes. We use these molecules with the carbon oxide double bond to could react to bonding with the perovskite material to passivation the surface. We deposit these molecules on the zinc oxide surface to before the perovskite depositions. We found that these materials introduced can enhance the emission a lot and also enhance the lifetime. And also these instrument materials can make sure the charge injection could be balanced. For the charge balance is very important for the light emitting diodes. For example, if the zinc oxide and the CPP as the electron and hole injection materials, the inorganic materials, the mobility is much higher than the organic mobilities. The electron charge injection should be much higher efficient than the holes. So the most of a charge could be to fast the holes. The most of a charge could be recombined in the whole injection layer. So we should reduce the surplus of the electron injection. So to make sure the balance of the charge injections. Based on this idea and also the passivation, we can at the 2016 we get over 10% efficiency for the very bright and very narrow emissions for the. And then second, we also used some molecules, we call it the TOPO on the surface to passivation the two-dimensional perovskite materials, and we can get 14% efficiency for this two-dimensional perovskite materials. And then even if the passivation is very effect, how about we passivation the perovskite surface and also the box? So we use when the perovskite the formation, we dropped this molecule onto the perovskite surface. This is the nuclear state. So this molecule can penetrate into the perovskite top surface and can passivation the perovskite materials and also the surface. We can get over 90% POPY for these green materials. And we can get over 22.5 efficient extra quantum efficiency for these green emissions. And the last part is the efficient and spectral stable perovskite blue emissions. The blue emission is always a challenge for each type of the light emitting diodes. And for the perovskite light emitting diode, for the blue in the blue regions, we know the blue. If we want to get the blue, the simple way is the mixture of bromide and chloride. Because the bromide, the emission is in the green, and chloride is maybe it's deep blue or some ultraviolet. So we should mixture these materials to the bromide and the iodide together to show the blue emissions. So there's some problems for the perovskite materials if we mixture these materials, especially for the bromide and the chloride too much. When the lighting or when we apply in the voltage, the spectrum will be shifted, and we call it the phase separations, because one is the bromide perovskite, one is the chloride perovskite. They be separated two phases. So this is the challenge. So how can we make sure the perovskite materials emission in the blue is stable? So we found some molecules when we don't use the mixture of the highlights such as chloride and bromide. We use some molecule, large molecule introduced in the A site because perovskite is ABX3, the crystal structure. We not use to X site to highlight site to control the band gap. We use A site to modulate the band gap. So if we from this material, the EA molecules can tune the band gap of the perovskite materials. When we greatly increase the amount of the EA, we can get very bright blue emissions. And also we confirm when we use these large molecules, when light is shining and also the heating, the spectrum of this material is always stable, even though maybe the intensity has been decreased, means this material has been degraded. However, the spectrum is still stable. So we also found this the large molecule has been incorporated into the perovskite layer to tune the band gap of. We also use the FDT, the theoretical calculations to predict to see how the band gap has been changed and how can use this molecule to tune the band gap. So based on these ideas, we can get the over 12% efficiency of the sky blue efficiency is not sure the blue is sky blue is the emission is 480 nanometers. If we also compare, if we use the highlighted mixtures perovskite, we can see if after increased the applied voltage, there's some shift for the NIST spectrum. So this has successfully demonstrated our method is feasible. It's for obtaining the blue emissions. Another question is, for the blue emissions, why it's still challenge? Because we know the perovskite materials, if the band gap, if the emissions is blue, the band gap is large. So the charge injection will be challenging. For example, some of the traditional charge transport layer, whole injection layer, such as the p-dot is 5.1. However, if you use the wide band gap, the materials, it may be close to 6 EV. So it's a challenge. This is a large barrier for the charge injection. This is one problem. The second problem for the perovskite materials, if you want to make high efficiency of the perovskite material, most of the time they use the two-dimensional perovskite material. What's a two-dimensional material? Is if we mix some composition together, they can form several type of the band gap. One is the wide band gap, one is no band gap. The charges come injection from the wide band gap and then cascade confine in the no band gap and the emissions. So the charge confinement efficiency will be very good. However, then also to some problem. The wide band gap we call it no end phase, where will increase the difficulty to the whole injection, because this has deep valence band and also very shallow conduction band. So we should balance. We should try to avoid too much of the no end phase. We call it the wide band gap phase. So how can we control the phase distributions into the least quasi two-dimensional perovskite? So we found a method when we introduce some materials into the whole transport layer. On the one hand, we can deep the valence band of the injection layers, so we can reduce the charge barrier, injection barriers, at least in the phase. And the second one, the phase, because the top layer, the bottom layer, injection layer had been changed. The perovskite form on this different surface should difference the phase distribution. When we use with the silicon chloride incorporate the whole transport layers, we see the small phase n equal to 1 in n equal to 2. These two phases, we can call it the no end phase has been suppressed. This means some wide band gap has been reduced, and this can increase the charging injections efficiency. So based on this idea, we got over 16% efficiency for the sky blue efficiency, the perovskite light emitters. Okay. Finally, I would like to summarize my talk. The first one, we have introduced some tin oxides as the planar structure to reduce the hysteresis in the planar structures. And also we found some molecules such as the PI itself could passivation the perovskite surface to reduce the surface recombination to increase the open circuit voltage of the perovskite solar cell. And also we found a new phase. This phase can replace the traditional lead iodide as the passivators at the grid boundary to make sure we can get high efficiency, and at the same time it can make guarantee the stable of the devices. And for the light emitting diodes, we introduce some molecules into the surface and also in the bulk, and also the passivation in the surface, including the surface and bulk, to reduce the non-radiative accumulation to enhance the perovskite light emitter efficiency. And we also, in the critical dimension, how can we control the phase distributions to optimize the phase distributions to make sure the charge injection efficient, and also make sure the charge confinement in the critical dimension is sufficient to make sure the efficient perovskite light emitters. Finally, I would like to thank my group members and also alumni for the cooperate, and also for the funding support for our research. Thank you so much.
Professor Jingbi You. Thank you very much. You're talking so passionately for a long time. It takes more than 1 hour.
Yeah, thank you so much. Maybe it's too much.
Yeah, thank you very much. And first of all, I'm very sorry because you cannot contact your questioner directly. So I will send, if someone has question, I will send you, okay?
Okay.
Yeah, so more than 73 students and professors are attending now. So if you have questions, please leave a question in the Q&A section in the bottom of the screen. I don't know where, but please give me a question. I will send you a question to the professor.
Yeah, I can see the questions from the screen. Yeah, if someone type the question in the, yeah, I can see it. Yeah.
Okay.
Now on the bottom, I can see the attendance and also the questions under the
I'm
chat.
sorry,
yeah.
I cannot see. I can see the questions. Okay. 질문. Okay, yeah. Thank you very much, Professor Jingbi You. I have several questions to you.
Yeah, I have the one.
Oh, yeah.
There's
one question. Yeah.
The first question is, do you have special reason for two-step method? Yes, it's good questions. Yeah, I think in HANA, we're always trying to use the one-step to deposition, because one step is maybe very efficient to make sure the composition is very accurate. So you can mix any composition you want. However, in the two-step, it's very challenging. However, for one step, it's challenging for us because the anti-solvent, the window is very level. So the several effect we factor maybe in the effect of the process. For example, the environment, the temperature, and the solvent, the environment, or other things. So maybe maybe now we still cannot find the optimize the conditions to the first step. However, we have the strong experience in the two-step, because two-step is net iodide. We can this layer we can control it very well, because net iodide cannot or the crystallization very fast if you use some solvent such as DMSO is the amorphous state or maybe the small crystal size. So the film is very uniform and smooth. So the control of the crystallization maybe is easier than the first step. At least for us, for our group at present. So I think the one step maybe is a very general message to make efficient the solar cells. As we are still trying to the first step, yeah. And the second question is, one step is really emotional, but two step is really what's the advantage? I think, yeah, this is the same question. The two step as for me, For the one step, it's excellent. You can go to very if you are a master in the one step, you can control and reproduce very good. For most people, if you're not very familiar with one step, maybe you cannot control it very well. Sometimes because the window is very sensitive to the environment. So for the two step, because the net iodide is gold for the perovskite depositions, the this scaffold is usually can reproducible and can be formed very good film. So it's not easy to form pinholes and also for the small particles or others. So this is this is my opinion. Yeah. The third question is
And yeah, Professor.
They say the chloride is maybe I think is different to another one because this chloride have some bondings with the lead, so they could be the passivation can be the more of them is the passivation. Or if they use the iodide and the bromide, if you can see this for the inorganic material, the solar cells, if the iodide perovskite, seasoned iodide, the perovskite, maybe the history is not very obvious. If we use if you use the bromide and iodide perovskite to make the solar cells, even though the reverse scan shows good performance, you can see if you cannot control very well, the history will be very large. This means the one maybe is the chloride and the bromide can be could lead to the phase separation or some others. I think the main reason is the increased band gap. The band gap may be there's much more opportunity to form the band, the several band states in the gaps. So this will correlate to the deep defect. I think this is my understanding for this one.
Yes, is another.
Yeah, another question is carbon, the double bonds in passivation materials. What's the problem? So I think, and this is maybe I think this is the similar of the solar cells. So the double carbon bond or the carbon oxide or the another bond the bonds. This means they could be some uncolored the electrons can be combined with the vacuum side of the net. So maybe they can passivation of the perovskite materials. However, there's no general mechanism to explain it. Maybe the sites and the chemical structures also affect of the passivation effect. There's some result, for example, the fungal and the porcelain has some results demonstrate different crystal structure, even though the similar is the carbon oxide, the double bond. However, some materials has passivation effect, some materials has no passivation effect. As for me, as for my understanding, maybe the structure or the configurations in effect of the passivation effect. This is maybe it's a little bit complicated. And no.
Yeah, there is no question. Any question? Any more question? No. Yeah. It's a long time, so I want to have one question about you. So yes, and in your recently published science paper, you make
Yes.
perovskite solar cell, but your main substrate is FTO, acai glass, okay,
Yes.
instead of
Yeah.
ITO.
Yeah.
So, but you make the tin oxide-based electron transfer using the spin coating method,
Yes.
not chemical best deposition, okay?
Yeah.
Yeah, how to make this uniform and thin thickness of the tin oxide layer by only using spin coating. Okay.
Yeah. Actually, you can see the tin oxide is very thick. It's 60 nanometers, maybe. I remember correctly. So I think in your papers you use just 20 or 30 nanometers. Yes, I think this is also the headache for our issue. You can see even though the fill factor is certified efficiency, the fill factor is 82. How the fill factor is 82. However, it's still much lower than you and also than So this still is the problem. The resistance the from the tin oxide, the resistance is still challenging for us at present. So we could improve it in the future. Yeah. So maybe you work with the conformers to make it very thin and can make sure the conformer. And so this could be the next directions for our improvement.
Yes, I would like to point this point to you, and also, I would like to have last questions. Maybe you said about the highest efficiency about the solar cell in your presentation, but how much solar cell will be increased in the efficiency increase in the future? What is your opinion?
Sorry about it.
Yeah, how much highest efficiency of perovskite solar cell in the future will be increased in the future, about 28%. How much efficient perovskite solar cell will be increased?
Yeah, I have mentioned maybe if we are very aggressive, maybe we should over than the silicon. Silicon is 26.7. We should close to the gallium arsenide because you see for the compare with the gallium arsenide, the difference is the band gap.
Yes, gallium arsenide is 27.73%. Maybe silicon-based solar cell, such as heterojunction solar cell case, is 26.7%.
Yeah, the silicon, the HI is 26.7. The gallium arsenide, the present high efficiency is 29.1. So I think for the comparing with the gallium arsenide, we can see that you say the open cycle voltage, the north, is close to the gallium arsenide. One at present is 0.32. Yes, and for the gallium arsenide, the real source is 0.3, so it's very close. I think at present maybe the challenge is how can we get the close to 100 as the quantum efficiency, because the gallium arsenide, the perovskite, the band gap is limitation is 1.5. The perovskite, the gallium arsenide is 1.42. So net material is the optimal SQ limit, they say. And another one is the fill factor. Fill factor, I think now it's close to 85. The perovskite maybe 18.7 or something like that. So this is our dream that we can working together to
yes.
Yeah.
I think so. Yeah, I want.
Yeah.
Yeah. Thank you very much.
Yeah, I think also there's some questions I can answer if the time is permitted. Yeah, why the net iodide increase the band gap of the FAPBI3? I think I have given a simple explanation. So for the net iodide is wide band gap material. So if you think about it, the easily, maybe it's the one reason. However, I think the main reason is the PBI tool could form a type 1 band gap alignment for the NIST 2 and type band alignment. There's some because this is quantum wall structures. There could be the band gap enlargement if you such like a quantum dots. If quantum dots reduce the size and also the strong confinement, the band gap will increase. However, if we reduce the amount of net iodide, the confinement, the effect will be reduced. So the F8 PBS3, the band gap will return to the back to its normal, to its intrinsic the band gap. I think maybe just my understanding. I'm not sure what's the reason. However, that's my understanding. And then
I'm sorry, Jingbi You, I would like to finish this webinar with this, okay?
Okay, no
we
problem.
spend more time, okay? Many times.
Okay.
So, yeah. And thank you very much for Professor Jingbi You, your wonderful talk. So please give him a big round of applause one more time, okay? And
Thank you
very
so much.
Yeah.
Thank you.
Okay.
Thank you.